Welcome to the Level 1 video on probability. We're going to start off today by talking about the expectation of a discrete probability density function. And I'm going to call it PDF just for short. Okay, so what is the expectation? The expectation is the expected value of capital X, and we write it as capital E of capital X. Okay, the expectation of X. And the formula is the expectation of X is the sum of our outcomes multiplied by the probability that capital X is X. And to illustrate this even further, let's look at an example of this. Suppose you roll a die and let capital X be the number on the uppermost face. Okay. Find the expectation of capital X, denoted the expectation of X. So our solution to this is, first of all, let's draw a table and here we have capital X and here the probability. Capital X is our outcome, so we have the numbers 1, 2, 3, 4, 5 and 6, and the probabilities are a sixth, and I'm running out of room, but all of them are a sixth. So our expectation of X using the formula is the sum of our outcomes multiplied by the probability. So this is 1 times a sixth plus 2 times a sixth plus 3 times a sixth plus 4 and 5 and 6 times a sixth. And this is 21 over 6, which is 3.5. So the expectation of X is 3.5. So that was a discrete expectation. What about expectation of continuous probability density functions? Okay, so if the probability now distribution of capital X admits a probability density function f of X which is continuous, then the expected value can be computed as the expectation is now the integral, not the sum, from minus infinity to infinity of our outcomes multiplied by our probability density function with respect to x. And the probability density function f of x must satisfy the following integral. That is that the integral from minus infinity to infinity of the probability density function with respect to x is equal to 1. And it's worth noting that the variance of capital X is the expectation of x squared minus the expectation of x all squared, and that the covariance of x and y is the expectation of x times y minus the expectation of x times the expectation of y. So let's work through a few examples. Example, the probability density function of a random variable x is f of x equals c times the exponential of minus 2x for x greater than 0. Find the value of c. So our solution to this we know that f of x must satisfy the integral from minus infinity to infinity of f of x with respect to x must equal 1. So the integral from 0 to infinity, as x has to be greater than 0, of c times the exponential of minus 2x with respect to x is c over minus 2 times the exponential of minus 2x, evaluated at infinity and 0. We're going to get c over minus 2 times the exponential of minus infinity plus c over 2, but of course the exponential of minus infinities go to 0, so we have that c over 2, and this has to equal 1, so it implies that c is equal to 2. And another quick example now. Suppose that a random variable x has expectation equal to 0.4 and the expectation of x squared is equal to 1.8. Calculate the variance of x, and our solution, using our formula from above, we know that the variance of x is the expectation of x squared minus the expectation of x all squared, so we get 1.8 minus 0.4 squared, which gives us 1.8 minus 0.16, so we're left with 1.64. So actually very simple to calculate, moving on with our theme of examples here, the table below contains the joint probability distribution and I'm going to call this JPD of two random variables x and y, and the table is the following. And the question is, what is the probability that x is 2? And our solution is that the probability that x is equal to 2 is 0.04 plus 0.10 plus 0.06, so just reading across that row, and that sums to 0.2. And another example, the table below contains the joint probability distribution of two random variables again x and y, so now the table looks like this, and the question is, what is the value of the expectation of xy, and also what is the value of the expectation of just y? So our solution to this is the following. The expectation of xy, so we have to do, let's make sure we can see the table, our outcomes multiplied by each other times the probability, and ignoring all the ones that are 0, plus 2 times 2 times 0.4 plus 1 times 3 times 0.1 plus 3 times 3 times 0.2, and summing all of this up we get that the expectation of xy is 4.8, and the expectation of y now is again the outcome times all the probabilities, 1 plus 0.01 plus 0.01 again, and we sum across all of this, 2 times 0.2 plus 0.4 plus 0 plus 3 times 0 plus 0 plus 0.2, and this simplifies to 2. And just one more example we're going to look at now. So again, the table below contains the joint probability distribution of two random variables x and y the table again for y and for x. Then the question is, given that the expectation of x is 2.1, the expectation of y is 2, and the expectation of xy is 4.3, what is the value of the covariance of x and y? And our solution is very simple, referring to the formula we spoke of above. The covariance of x and y is the expectation of x and y minus the expectation of x multiplied by the expectation of y. So we get 4.3 minus 2.1 times 2, which simplifies to 0.1. Thanks very much for listening.